Section 6.4 is about the Gram-Schmidt process. Now, the Gram-Schmidt process, is basically used to create an orthogonal basis for some subspace W. And the idea is that we just keep creating orthogonal projections, and then the leftover orthogonal components become elements of the basis. So we just keep doing orthogonal projections over and over and over again. All right. So let's just go ahead and do this. Let's find an orthogonal projection of y onto v. So the projection of y onto v, where y is 3, 1 and v is 1, 1. And then let's find the orthogonal component, or excuse me, the component z of y orthogonal to v. Okay? We've done a lot of projections. I'm just going to go through that pretty quick. If you need a refresher on that, go to a previous videos. But I think we've done this problem before. So projection of y onto v, we'd take the inner product of y and v divided by the inner product of v and times v. Again, the inner product of v and v. That's going to be our coefficient, and then we're going to multiply that times the vector v. When you do that, you end up with inner product of y and v is 3 plus 1, which is 4. Inner product of v and v, that's 1 plus 1, that's 2. So 4 over 2 times the vector v, which is 1, 1. So you end up with 2, 2 is the projection of y onto v. So 2, 2 is the projection of y onto v. And because of that, if you look at the component z, which is orthogonal to v, we're going to go 3, 1 minus 2, 2, which is 1, negative 1. Now, what I want you to see is that z, because it's the orthogonal component, z is going to be orthogonal to the vector v. And the real trick is to see that anything that I can write as a linear combination of y and v, I can also write as a linear combination of z. Let me show you that in just a second. Before I do, this is what I'm saying. So first off, we're going to do an orthogonal projection. And I claim if you look at the set Vy and then take the span of those two vectors, I claim that is exactly the same as the span of Vz. Moreover, because of the way I found z, z and v must be an orthogonal set. So Vz is an orthogonal set whose span is the same as Vy. Now let me show you that the span of Vz is the same as Vy. All right, so let me go into the projection, and let's just call the projection what we called it before. This was a bit ago. Let's call it y hat. So the projection of y onto v is y hat. And we can see that y hat is just 2 times my vector v. All right? So anytime we see a y, it is y hat plus z. Hopefully that makes sense. Y can be always replaced with a y hat. Whoops. Y hat plus z. All right. So now let's think of a linear combination. Let's think of the span of Vy. So anything in the span of Vy can be written as, oops, a linear combination of V and Y. So we go, I don't know, let's take some element in the span. Let's call it C1V plus C2Y, where C1 and C2 are just real numbers. Well, what I can do is I can say that that is going to be the same as C1 times V plus C2 times Y hat plus Z. So Y we just saw from before is Y hat plus Z. Y hat is just 2 times V. So now what I'm going to do is I'm going to take this whole thing and I'm going to replace Y hat. I do not know what's going on there. I apologize. Something's weird with the copy paste tool there. All right, so we get that. So this whole thing is Y hat, we said, is 2 times V, as in the real number 2. We should make these real numbers unbolded. And then obviously if we distribute C2 and regroup, what we see is that, well, I'm going to do some combining. C1 plus 2C2 are all being multiplied times my vector V, and then C2 times my vector C. So C1 plus 2C2, that's just a real number. C2 is just a real number. And so there you go. Anything that can be written as a linear combination of V and Y can also be written as a linear combination of V and Z. Moreover, V and Z are orthogonal. So if Vy is a basis for some subspace W, then Vz is an orthogonal basis for that same subspace W. And there you have it. So that's the idea. So instead of using Y, we replace Y with the component that is orthogonal to V. So I do the projection of Y onto V, find the piece that's orthogonal, and then we're off to the races. This VZ must be an orthogonal set, and moreover, it's a basis for the subspace, which is the span of V and Y. So that's the big idea of the Gram-Schmidt process, or excuse me, that's the general goal. And the Gram-Schmidt process is just the process behind doing that over and over and over again. So here's the big idea. We're going to start with some basis, and we're going to start creating an orthogonal basis. So what we do is we take x1, we set it equal to v1. And when I say that, so this original basis, x1, x2, x3, x4, may or may not be orthogonal. we're going to create a basis V1, V2, V3, V4, which is an orthogonal basis. So what we do, we start with x1, we set that equal to the first element of my new basis. Now, normally, if we were going to add a new element to the basis, we'd add x2 to this set. But if I just add x2 straight up, x2 might not be orthogonal to x1. So what I do, instead of adding x2, we add in the component of x2 that's orthogonal to v1, and then we call that v2, the second element in our orthogonal basis. Then we let x1, x2 be. Now, since x1 is equal to v1 and v2 is the orthogonal component with respect to x2, we know the span of v1, v2 is the same as x1, x2. So instead of adding x3, we add in the component of x3, which is orthogonal to the span of v1, v2. And then we do that same process. We, instead of adding in x4 into the set v1, v2, v3, we add in the component of x4 that is orthogonal to this set v1, v2, the span of v1, v2, v3. Hopefully that makes sense. So in each entry, we're just adding a vector into our set, and we do that over and over and over, and it's always the vector that is orthogonal, or at least the component that's orthogonal to the span of the set we've already created. Now, formally, it looks like this. V1, so we start with the basis, x1, x2, x3, x4. We let V1 be x1. V2 is going to be x2 minus the projection of x2 onto v1. All right, that's what this is. The projection of x2 onto v1, we take x2 minus that, and that gives me my orthogonal component, which we call v2. When we go to v3, we let v3 be x3 minus the projection of x3 onto v1 minus the projection of x3 onto v2. Okay, which again is the orthogonal component of the span of v1 and v2. So the component of x3, which is orthogonal to the span of v1, v2. Now, by the way, these all have to be non-zero because, as we said, our original basis, we said, was an actual basis. So if we ever have a 0, that would mean that x3 would have been exactly a linear combination of v1 and v2, which again contradicts the fact that this basis is linearly independent. Now, I wrote 4 elements in this basis, but you can go as long as you want, right? You can do this process over and over and over, and every time you're going to find a new VP. You're going to take your XP minus the projection of XP onto V1 minus the projection of XP onto V2 minus the projection of XP onto every V that was already put there. And then my final basis, V1 through VP, will be orthogonal and will have the same span as X1 through XP. Again, I wrote 4 down in the previous slide, but you can go on as many as you want. So let's take and use the Gram-Schmidt process to find an orthogonal basis for the following subspace. Now, I do want to mention, before I get into this, that it will matter which one you call x1 and which one you call x2 and which vector you call x3 and which vector you call x4. Okay? On homework problems, I'm always going to call the first one x1 and then the second one x2, and so it'll be in order. So when I get to a question like this, 1, 1, 0, 5, 2, 1, I'm going to call x1 1, 1, 0. And x2 I'm going to call 5, 2, 1. So hopefully that makes sense. That's how we're going to play it. All right, so here we go. So during the Gram-Schmidt process, what I'm going to do is I'm going to say V, let's make that bold. So I'm going to say V1 is equal to 1, 1, 0. All right. So my first element in my orthogonal basis will be 1, 1, 0. Now if I just throw in x2, that's going to be troublesome. So what I'm going to do is I'm going to throw in, instead of x2, I'm going to throw in what I'll call v2, which is just x2 minus the projection of x2 on to v1. All right, so we have to take the projection of x2 onto v1. Don't forget how to do that. Inner product of x2 and v1. Inner product of v1 and v1 multiplied times v1. Okay, so if we just calculate this, this is the component of x2, which is orthogonal to v1. So let's go ahead and do that. So v1 is 1, 1, 0. x2 obviously is 5, 2, 1. All right. So let's take a look at that. Never bolds. So we're going to take 5, 5, 2, 1 minus. Now the inner product of x2 with v1, 5, 2, 1, inner product with 1, 1, 0. I get a 5, I get a 2, and I get a 0. So I get 7 over inner product with v1 times itself is 2 on to v1. V1 is 1, 1, 0. So if you do your calculation, you get 5 minus 3 halves, or excuse me, not 3 halves, 3 and a half. So you get 1.5. You get 2 minus 3.5. So you get negative 1.5. And then you get 1. So there you go. V2 is 1.5, negative 1.5, 1. So what we've done is we've just created an orthogonal basis for my subspace, and my orthogonal basis is going to be the set containing V1 and V2. There you go. Those two elements have the same span as my previous set did, and these two elements are orthogonal. Now, one thing about this that I will add here is that orthogonality and linear combinations are not dependent upon which scalar we pick. So what I could have done on this is, once I have my orthogonal basis, I can actually create infinitely many orthogonal bases with the same span by just taking different multiples of those two elements. So for instance, you could have taken, 2, 2, 0, and 1.5, negative 1.51. Similarly, you could have taken their second element, 1.5, negative 1.51, and multiplied it by 2. So I will say that multiplying by a constant will not change the orthogonality, okay? Now, this is important, again, when you do homework and things like that. When you do homework and you're plugging in your answer, always plug in this version here. But in reality, sometimes we like to scale it so that these entries are whole numbers. Like we might have multiplied this one by a 2 so that all of our entries, 3, negative 3, 2, are whole numbers. Okay, but again, on your homework, we're going to type in this first vector. Excuse me, this as your x1, which is v1, and this as your v2. So I want you to push pause on the video and try to use the Gram-Schmidt process to find an orthogonal basis for the following subspace. Right, so here we are. Hopefully you push pause and did all that. So what we're going to do is we're going to go x1 and x2. x1 in my case is 213 because it came first. x2 is 471, came second. By the way, if you would have switched those roles, you would have still gotten an orthogonal basis whose span is the same span as that subspace, but it would have just came out to different vectors. So you can do this either way, but again, to be consistent, I'll always label things left to right as x1, then x2, then x3. So x1 is 213, so v1 has to be 213. Now, instead of adding x2, what we're going to do is look at x2 minus the projection of x2 onto v1. So what we have to do, x2 is 471. So we take 471 minus, now here's the tricky part, coefficient, inner product of x2 and v1. 4 times 2 is 8. 7 times 1 is 7. 1 times 3 is 3. So 8 plus 7 plus 3 becomes 18. And then v1, inner product with itself, you're going to get 4, 1, 9. All right. So 419 added up gets you 14. So we get 18 divided by 14 times V1. That's the projection. So this is the projection of x2 onto V1. So if I take x2 minus that projection, you're going to get the component which is orthogonal to V1, and that will be my second element in my set. Now, in this case, notice we're going to get some ugly fractions, and that's perfectly fine. When I take my first entry, 4 minus 18/14 times 2, I get 10/7. When I take 7 minus 18/14 times 1, I end up with 47. And when I take 1 minus 18/14 times 3, I end up with minus 20/7. All right. So my two vectors in an orthogonal basis are going to be 2, 1, 3, and then 10 sevenths, 40 sevenths, negative 2 sevenths. Now, if this orthogonal basis kind of throws you off because of the sevenths, obviously you could have kind of rounded decimals. The online homework asks you to do things in decimals when you get ugly answers like that. But you could have also scaled that orthogonal basis by just multiplying this by this second vector by a 7. Whoops. You'd get 10, 40, negative 2. And in fact, you could have divided everything by a 10 or multiplied everything by 1/10. 1, 4, negative 2 will also give you an orthogonal basis. By the way, you can check this one a lot easier. Take the inner product. 2 times 1 is 2. 1 times 4 is 4. 3 times negative 2 is negative 6. So 2 plus 4 minus 6 is 0. So you can check that that is, in fact, orthogonal. A little bit quicker than using the sevenths. So there you go. So in reality, you can use either of these two bases to be orthogonal. Again, on the test, it's going to be asking you for this one. Now we're going to keep that in the back of our head, and I want you to try this one on your own as well. Use the Gram-Schmidt process to find an orthogonal basis for the following subspace. All right, so hopefully you went ahead and pushed pause and did that. So here's what we're going to do. Use the Gram-Schmidt process with x1 is 8210 and x2 is 2364. So first off, we say, which is our first element that I put in my basis? I always go with x1. So go 8210. That's the first element that I put in my basis. My next element that I put in my basis is going to come from projecting x2 on to v1 and then taking the remainder. So I take x2 minus the projection of x2 onto v1. Now, this gets a little bit hairy, but that's okay. x2 is 2364. When I take the inner product of x2 and v1, 2 times 8 plus 3 times 2 plus 6 times 1 plus 4 times 0, I end up with 28. And when I take the inner product with v1 times itself, that's going to be 8 times 8 plus 2 times 2 plus 1 times 1 plus 0 times 0. 64 plus 4 plus 1 gives me 69. So the coefficient of v1 will be 28 over 69. So I'm going to take my x2 minus 28 over 69 times v1. And when you do those calculations, you end up with negative 86 over 69, 151 over 69, 386 over 69, and 4. Just the whole number 4. So there you go. So what we have now, we've created an orthogonal basis. The 8210 is going to be my first element. And my second element is going to be negative 86 over 69, 151 over 69, 386 over 69, and 4. Now, if you don't like the fractions here, what you could do is you can multiply all of those entries by 69. And if you multiply all of those entries by 69, you get negative 86, 151, 386, and then 4 times 69 is 276. So if you feel more comfortable with whole numbers, you can always scale up. Again, when you're writing answers in the homework, write this answer in decimal format, but in a test setting, by all means, sometimes whole numbers are much easier to deal with. By the way, if you want to test this out, test and check, do your inner product and see if these two are in fact orthogonal. And by the way, they will be. Now the question comes up, what if we have 3 elements? What if we have like a 1, 1, 1, what excuse me, 1, 1, 0, 5, 2, 1, 4, 2, 4. Now, interestingly enough, we've already dealt with the span of these first 2 vectors, 1, 1, 0 and 5, 2, 1. We've used the Gram-Schmidt process to find those. And notice that the first 2 steps of the Gram-Schmidt process don't change given my basis size. You always set V1 equals x1. You always set V2 to be x2 minus the projection of x2 onto V1. So the first 2 steps don't change. So when we're dealing with this set of 3 vectors, we might as well use what we had from the previous result. Let me go through that again. Like I said in the previous slides, we had 1, 1, 0, 5, 2, 1. We did our V1 is equal to x1, so V1 was 1, 1, 0. V2 was x2 minus the projection of x2 onto V1. We ended up with that V2 was 1.5, negative 1.51. And we said, well, that's our orthogonal basis when I had 2 basis elements. Now, all I do is I say I want to go and make a V3. So I'm going to do it in a very similar way. V3 is going to be similar to V2, except now I'm going to have to do 2 projections. So I'm going to do an X3. I'm going to project X3 onto V1, and I'm going to project X3 onto V2. By the way, I can do this because right now I've forced V1 and V2 to be orthogonal. So this only works because I've forced V1 and V2 to be orthogonal. In fact, dang it, I think I've messed this up. I think that when I did on my slide previously, I started with subtracting V1. It's all the same, but I forget if I started with V1 and ended with VP or if I started with VP and ended with V1. But again, you're subtracting the projection of X3 onto V1 and the X3 projected onto V2. All right, so there you go. Now, in this situation, let's go back to the slide. So the slide looks like this. And we have our x1, our x2. 4, 2, 4 is our x3. So going back to our worksheet, x3 is 4, 2, 4. We've already found v1 to be 1, 1, 0 and v2 to be 1.5, negative 1.51. So all we have to do is take 424 minus the projection of 424 onto 110 minus the projection of 424 onto 1.5, negative 1.51. Now in this situation, if I take inner product, 4 times 1 is 4, plus 2 times 1 is 2, plus 4 times 0 is 0. I end up with a 6 divided by V1 times itself. 1 times 1 is 1, plus 1 times 1 is 1, gives you a 2. By the way, 6 over 2, we could call that a 3 if we'd rather. If we go 4 times 1.5, 4 times 1.5, when I'm projecting 4 to 4 onto 1.5, negative 1.51. So I'm taking the inner product of x3 with v2. So 4 times 1.5 is 6. You're going to get 2 times negative 1.5, that's a minus 3. And then 4 times 1 plus 4, which gives you a 7. 6 minus 3 plus 4 gives you 7. Whoops, did I say 7? I wrote 6. Yeah, 7 over 1.5 times itself plus negative 1.5 times itself plus 1 times itself. That gives me a 5.5, 5.5 there in the denominator. So there you go. That's what V3 will be. Now with some simple calculations, 4 minus 3 times 1 minus 7 over 5.5 times 1.5, you're going to get a straightforward vector. Let's see if I can just calculate that. So 3 by 1 vector, we got 4 minus 3 times 1 minus 7 over 5.5 times 1.5. It's kind of a long deal, but that's what it is. When I simplify that fraction, I get negative 10 elevenths. Actually, let me do this just so I can write it on a different line. All right, I won't go through every one like that, so let me do the calculations here. What I'm saying is once you do the calculations, 2 minus 3 times 1 minus 7 over 5.5 times negative 1.5 actually gives you a 10 over 11, positive 10 over 11. And then when you take 4, that would be minus 0 minus 7 over 5.5 times 1. I ended up with a 30 elevenths. Okay, so if you add that to the set we had before, now we would have an orthogonal basis for our space. So there we go. So we take our original orthogonal basis, now we just add another vector. And by the way, if you do the inner products, you should find that this is an orthogonal set. By the way, moreover, if you wanted to scale these to a little bit nicer things to look at, obviously you could. You could, like we did before, scale this first vector to 3, 3, I'd say it first, I apologize. The second vector to 3, negative 3, 2. Notice that if you multiply everything by 11, the denominators go away here. If you divide everything by 10, you get negative 1, 1, 3. And go ahead and just convince yourself that this is an orthogonal set. 1, 1 times 3, negative 3. Yep, that's going to give you 0. 1, 1 times negative 1, 1. That's going to give you 0. 3 times negative 1, that's negative 3. Negative 3 times 1, that's another negative 3. So you get minus 3, and then 2 times 3 is plus 6. So yes, all of these vectors are orthogonal to one another. So you can scale it at any time. In fact, if you would have rather, you could have scaled the 3 to, could have scaled to 3, negative 3, 2, sort of midway, instead of using 1.5, negative 1.5, 1, you could have scaled to 3, negative 3, 2 at that stage to make your life maybe a little bit easier. And that's what I would do for the next process. Now, what I'd like you to do is I'd like you to use the Gram-Schmidt process. We're going to keep these two vectors the same, which is going to force us to have the same v1, v2 that I just did. But I want you to switch that last vector to 8, 5, 1. So let's find an orthogonal basis for the subspace 1, 1, 0, 5, 2, 1, 8, 5, 1. Go ahead and push pause on the video and see what happens. All right, so let's go to projection. Now my V1 and V2 are the same. I'm going to use 1.5, negative 1.51. If you ended up using 3, negative 3, 2, that's no problem. You're going to get the exact same answer in the end. Okay? Again, scalars aren't going to hurt anything. So scaling your vector at any stage is okay. So let's take 8, 5, 1 and project onto V1. So when we project onto V1, 8 times 1 is 8. 5 times 1 is 5, so 8 plus 5 is 13. So you get 13 over 2. When you go 8 times 1.5, oh, let me actually, sorry about that. Let's finish this up. So 8 times 1, 5 times 1, 1 times 0 gives you 13. That's the inner product x3 with V1. V1 inner product with itself becomes 2. We saw that from last time. Now let's project x3 onto V2. So inner product of x3 and V2, 8 times 1.5 plus 5 times negative 1.5 plus 1 times 1. And you end up with getting 5.5 over 5.5, which obviously can be reduced to 1. And by the way, if you want, 13 over 2 can be reduced to 6.5, or it can be simplified to 6.5 if you'd like as well. So V3 is going to be x3, 851, minus the projection of x3 onto V1, minus the projection of x3 onto V2. Now, when you look at this, turns out really interesting. 8 minus 6.5 times 1 minus 1 times 1.5 ends up as a 0. 5 minus 6.5 times 1 minus 1 times a negative 1.5 also ends up as a 0. And 1 minus 6.5 times 0 minus 1 times 1 also ends up as a 0. So V3 gives me the 0 vector. Now, all that really means is that this set that I started with was not an actual basis. This set was linearly dependent. 851 can be written as a linear combination of these two elements here. So that doesn't mean the Gram-Schmidt process is wrong. What that means is that when we're looking for an orthogonal basis, we basically just have to throw out that V3 that we just found. So we had 0, 0, 0. We obviously cannot use 0, 0, 0 in a set with a basis. So we say an orthogonal basis is just these two, the set containing these two vectors. So our subspace W only had dimension 2. So that's what's going to happen if we have an x3 which is linearly dependent upon x1 and x2, which means it would be linearly dependent upon v1 and v2. We get a 0 vector, and then we just ignore that in our set. Now that's not going to come up a whole lot, but it could come up. Now, earlier we found an orthogonal basis for the span of the first two elements of this set. I want you to find an orthogonal basis for the span of all three elements of this set. Go back and use your previous work when we found the orthogonal basis for 8, 2, 1, 0 and 2, 3, 6, 4. By the way, use the one which has the nice numbers. Don't use the one with the ugly fractions. Use the one with the nice numbers and go ahead and find an orthogonal basis for this span. Push pause on the video and do that. Hopefully you went ahead and did that. This one obviously, well, we had some crazy looking vectors before. Remember our first two vectors when we did the Gram-Schmidt process from before were 8, 2, 1, 0, and negative 86, 151, 386, and 276. Now, if these can be simplified in a nice way, you can try that, but I don't think that they can. So those are the two vectors we're going to deal with. By the way, if you recall, that second vector, we had uglier fractions, and we multiplied everything by 69. So this is the slightly better version of V1 and V2. So this is the set containing V1, V2. As always, V3 is going to be our third vector minus the projection of the third vector onto V1 minus the projection of the third vector onto V2. Now you get some real doozies for coefficients, but that's the way the world works sometimes. So x3 is negative 2, 4, 3, negative 1. When I project that onto 8, 2, 1, 0, when I do the inner product of negative 2 times 8, 4 times 2, 3 times 1, negative 1 times 0, I end up with a negative 5. 8 times 8 plus 2 times 2 plus 1 times 1 is a 69. When I project x3 onto v2, negative 2 times negative 86 plus 4 times 151 plus 3 times 386 minus 1 times 276. What I ended up with is 1,658. When I take V2 inner product with itself, that's going to be 86 squared plus 151 squared plus 386 squared plus 276 squared, which I got out as 255,369, 255,369. Now that is an ugly fraction, but that's no problem. We can put all these things into our calculator. So -2 minus -5/69. I'm just going to call that plus 5/69 times this vector minus 1658 over 255,369 times this vector. What I ended up with, and then I converted to fractions, was a -3190 over 3701. And then I ended up with 11712 over 3701, 2096 over 3701, and then -10,333 over 3701. So there you go. That's your vector V3. Now obviously, when you plug it in to your set, you might want to use whole numbers, even though they're really big whole numbers. That's still okay. So you might go with the scalar, might multiply everything by 3701 if you'd like. Makes it just slightly better. Although, again, still we're getting some big numbers here. By the way, if you check, you can check and to see if this is an orthogonal basis. Go ahead and do that if you'd like. This is an orthogonal set, and it is going to have the same span as this set here. So that's how you project, or that's how you create an orthogonal basis for any subspace using the Gram-Schmidt process. We start with a generating set like this one, and then do our projections. Now, one thing that sometimes people like to do is they like to create orthonormal bases. So the idea of orthonormal has come up before. It's basically an orthogonal basis where every vector has length 1. So if we are in a situation where we don't want just an orthogonal basis, but rather we want an orthonormal basis, we basically just use the Gram-Schmidt process, and then at the very, very end, we scale everything to make it length 1. So let's do this one, for instance. We have 2, 1, 3, 4, 7, 1 as a generating set for some subspace. And we actually already have done this problem. We've found an orthogonal set, which is a basis for this subspace. So we're going to go back and look at that and then find an orthonormal basis for this subspace. All right, hopefully that makes sense. Okay, so here we go. So we started with 2, 1, 3, 4, 7, 1. And again, I'll go through it again very, very quickly. We let V1 be my 2, 1, 3. V2 is going to be the leftover part when I take x2 minus the projection of x2 onto V1. That turned out to be 10 sevenths, 40 sevenths, negative 20 sevenths. And I said, well, that's our orthogonal basis, 2, 1, 3, 10 sevenths, 40 sevenths, negative 20 sevenths. But also 2, 1, 3, 1, 4, negative 2. If I just scale this vector, that's an orthogonal basis as well. So that's the one I'm going to start with. So we have this as our orthogonal basis. We want to make it an orthonormal basis. So I'm going to take 2, 1, 3 and say, well, the length of 2, 1, 3 is going to be 2 squared plus, plus 1 squared plus 3 squared. So if you calculate that, 2, that's 4 plus 1 plus 9, which is 14. Again, what I'm doing there is I'm just taking the inner product of 2, 1, 3 with itself, and then taking a square root of that. So square root of 14 is the length of 2, 1, 3. Which is what vector we're calling v1 now. All right. Now, in a similar way, you can go 1 times 1 is 1, 4 times 4 is 16, 2 times 2 is 4, so, you end up with 21. So square root of 21 is the length of V2. All right, so all we have to do is scale this appropriately. And by the way, how we scale each vector is we just go 1 divided by the length. So all we're going to do to find an orthonormal basis we take 1 divided by the square root of 14, multiply that by 213, and then take 1 divided by the square root of 21, and multiply that times 1 for -2. And there you go, that's my orthonormal basis. Now if you want to clean that up a little bit, you can. Let me go and type that separately. So if I distribute the 1 over square root of 14 into 213, I get 2 over root 14, 1 over root 14, 3 over root 14. If I distribute the 1 over square root of 21 into 1 for -2, I get 1 over square root of 21, 4 over square root of 21, -2 over square root of 21. Again, not very interesting, but there you go. Okay, if you're doing this on a test or something, it's perfectly fine to just leave this coefficient out front times 2, 1, 3, and this coefficient out front times 1, 4, -2. Now you can do that with any set you'd like. So let's do the set we just found. Let's use the previous Gram-Schmidt, well, we used the previous Gram-Schmidt process to find an orthogonal basis for this. I want you to go back and change that orthogonal basis into an orthonormal one. So push pause on the video, go ahead and do that. Again, these are going to be some big numbers, but that's perfectly all right. All right, so hopefully you went ahead and did that. Again, you get some big numbers, but the point is not the numbers, it's just to see the concept that once we have that orthogonal basis, so we found this orthogonal basis, now we can simply say, well, what's the length of this V1? That length of V1 is square root of 69. Again, if you take the inner product of V1 times itself, you get 69. So the length of V1 is square root of 69. V2, you look at all those numbers, the length of is going to be the square root of the vector inner product with itself, which turns out to be the square root of 255,369. And then as far as V3 goes, V3 has the biggest numbers. Now again, I'm using the version without the fractions. You can use the version with the fractions if you'd like. But without the fractions, we get this as the square root. That is 258,511,149 under the square root symbol. Now, no matter how ugly these numbers are, the orthogonal basis can be converted into an orthonormal basis by just taking 1 over the length times each vector. So 1 over the square root of 69, 1 times vector 1. Vector 2, I'm going to multiply 1 over the square root of 255,369. Again, that's times vector 2, and then 1 over the square root of 258,511,149. Okay, I'm obviously not distributing that. I don't think we need to deal with distributing that in this case. Okay, it's pretty ugly looking thing already. So there you go. Those three vectors would all have length 1, as ugly as they look. They'd all be orthogonal to each other. And they would be the A basis for this set here. So this subspace there. So that is the Gram-Schmidt process. Okay. Now, when you're typing things in to the homework on Moodle, be very careful of how you type things in. Read the question. Sometimes I think it asks you to round decimal places and things like that. Okay. But always start with x1 as your left-handmost vector, x2 is your middle, x3, so on and so forth as you go to the right. So hopefully that all makes sense. That is it for what we're going to go over in Chapter 6. The Gram-Schmidt process, remember, generates these orthogonal bases. And the orthogonal bases are really important in the idea of finding orthogonal projections. So that wraps up Chapter 6 for us.